it might be fixed at this point. I'm just getting some messages that people have been completing things, but that doesn't mean it's working completely yet. So sometime today, I don't have a lab today, so I'll be able to work on that around 2 o'clock. So if it's not in Canvas, you'll get a message that quiz is in Teams.
And when will it be due?
It'll be due before class on Monday.
Okay.
I'll send a message to you guys.
What them test results looking like, Doc?
We'll talk about that. So there's a couple things with the test because Canvas messed up. I can't see all of the stuff yet. So I can only grade partially some of the exams. Some of the stuff that came in person, they don't look too bad. Okay, but some people missed the parent chain on a lot of questions. We'll talk about that. And I got some students that are still needing to complete the test. So I don't want to talk about it until I get everyone situated. But hopefully that'll be soon. Hopefully this weekend I can work out all the last minute stuff and we can have that exam in. You guys should be getting a few messages if Canvas is working. I already put those messages in to be released at the end of class, but because Canvas is messed up, you might not receive them. So I'll try to make sure you get the messages. But exam 3 is coming up soon. It's going to be November the 9th. It's going to cover chapters 4, 6, and 7. I know that seems like a lot, but it's not. You guys kind of see that here shortly. We're pretty much near the end of chapter 6, and chapter 7 is just the opposite version of chapter 6 reactions. All right. So we're getting to a good place where we're ready to take that exam. And then the final exam will be right before you guys leave for Thanksgiving. It will cover the last 2 chapters. And the strategy for the last 2 chapters is just to learn the reactions and kind of have those reactions committed to memory. You know what the reagents do. You know how to predict the major products. If you can do that, you are going to be set up well for second semester organic. Okay. So with that said, let's kind of move forward with chapter 6 material. All right, so we're working on a new class of reactions. This is the first time we talked about this, and it's called a substitution reaction. All right, so let's look at the substitution reaction really closely here, or at a fundamental level first. If you think of substitution, what do you think that means to you?
Substitute, replace something with another one without harming it in any way.
Exactly. That's dead on. If I'm substituting, I'm going to replace you with something probably better if I can, right? That's how people think of substitution. All right. So the first thing to keep in mind, and this is why this reaction is covered in chapter 6, all right, is that I'm starting off with a compound that has X. And what does X mean? Can anybody help me out? When I'm referring to X, what am I really trying to say? I already drew it in here, but that's group 17, halogen. That's right. So chapter 6 is dealing with alkyl halides, right? And we want to keep in mind what is an alkyl halide? Can anybody break that down for me? What's an alkyl halide?
Basically, like single bonds with halogen attached.
Yeah. Carbons with halogens. You can even simplify this as just saying, yeah, most people think of all carbon single bonds. But if I have a carbon bonded to a halogen, it's an alkyl halide, right? Chapter 6 first deals with how to make those compounds. So how do you make alkyl halides? Can anybody help me out? This is what your quiz is going to cover. These come from free radical halogenations, right? Everybody remember?
So is the X representing something like that?
X is representing any halogen. Fluorine, chlorine, bromine, iodine, etc. All right. So a free radical halogenation to any alkane, I'll say that here, right, will produce an alkyl halide. Do we need to see an example of that? Or are you guys comfortable with that?
Could I see an example? Just a visual. Just so.
Okay. Give me a sec here. Trying to move this thing down. Boy. But maybe I'm being too picky. All right, I'm gonna do this for you. I think that's Mr. Smith talking. I'm gonna show how we make the alkyl halide in the next step. Just because I started on substitutions, I want to kind of go ahead and finish the thought first, and then we'll work on that.
That's cool.
Okay, so just for now, I can make any alkyl halide from a free radical halogenation to an alkene, and we saw that material in our chapter 4 in the beginning of chapter 6. All right, there's going to be a term that I'm going to use here, and we'll define it here shortly, a nucleophile. And typically, I like to abbreviate this as NUC. I like to put it in brackets. So if I take an alkyl halide and I introduce it to a nucleophile, and the solvent is going to be very important for these reactions now, so I'm going to indicate the solvent, I'm going to end up doing a substitution. So instead of having a carbon halogen group, I'm now going to have a carbon bonded to a, make it so big, nucleophile. And there's going to be a leftover molecule X here. This is a 24 font. All right, let's keep this green. Let's change this into a red color here.
So it will be a leftover of whatever halogen you started with.
Yep, this is going to fall off, but typically it's not X minus, it's going to be a salt. We'll talk more about that in particular, but for the general case, that's going to leave as a leaving group. All right, we'll talk about the names of these things here shortly. All right, so in a general sense, this is how a substitution will work. I need a compound that has an alkyl halide. I need to have a nucleophile. And if these two things react, I'm going to substitute the halogen for a nucleophile bond. Let's see if I can get an arrow to help here. Right, so this is where that substitution is occurring. All right, any questions so far on just generally what a substitution reaction is? All right, let's go ahead and let's draw it.
No, I think that was pretty simple. It just substituted what was given, right?
Yep, with a nucleophile. That's exactly right. And we'll break down this nucleophile here shortly. So I want to do some substitutions to this compound. But before we do it, because a great question came up, how do I make this compound? Right? That's what you guys want to remember. How do I even prepare this thing here? So I'm going to start off with my 4-carbon chain here, which is named what? Anybody help me out? I have 4 carbons in a row. What's the name of this molecule?
Tetra.
Butane, right?
Butane.
Good. All right. So how do I convert butane, which would be which functional group? What would you call this functional group? Is that somebody in Teams? Messaging me? I'm getting the students in now. This is known as an alkane, right? Functional group. All carbon-carbon single bonds. How would I get butane? From petroleum, right? So there's some fossil fuels, there's some prehistoric animals or plants that got compressed and preserved in the earth crust, right? They kind of make this oil. We pump the oil out, and the oil contains all these random chains of hydrocarbons, right? And so why would that happen? Because those molecules or those organisms that died were organic, right? So even if we died and our body was preserved a certain way, somebody can reuse all of the fatty acid chains in our bodies and things, right? And just distill them to get all these different things, right? But conveniently, from those prehistoric animals, we get crude petroleum and butane, would be one of the gases that we could capture. All right, so we get this from a natural source, and I need to make this molecule here. How would I do it? Can anybody help me out?
Would you put bromo and light?
Yep. I would do a free radical halogenation here, right? So if I took bromine and I shine it with some light, or heat will work as well, but because generically we're just saying any energy. But most people like to use blue light. I'm big on that type of chemistry. Then I'll get a free radical halogenation. Keep in mind that the more stable radical is going to be which one? The secondary radical, right? So there's two potential sites, A and A and B and B. But the secondary radical is going to be the most stable one. Right? So this is going to be the reactive intermediate that leads to the final compound.
Can you explain that part again?
Can I explain which part again?
When you started adding the free radical, like that very last part.
This is okay. I guess the thing here that you wanted to see was that this is the radical that got terminated to form this final product, right? So the steps are Br is gonna break homolytically to form two bromine radicals. Bromine is gonna extract the hydrogen, right? All these carbons have hydrogens that could be extracted. All right. So since I got this product, all right, I need to figure out why I got the bromine here and not there. And the reason is because if I pull an H from this carbon, it will lead to a secondary radical. If I pull the H from this carbon, it'll be primary. All right, you guys want to also recognize that there's symmetry here, right? The carbon here and the carbon there are identical. So the carbons on both ends are the same, right? And the carbons that are in between here are also the same. So there's only two potential sites you can brominate, right? So in this case here, this radical leads to that product, and this is the most stable radical possible in this reaction. Does that answer your question?
Yes, but one more question. So it doesn't matter if you would have put the radical on the other like dip point rather.
Nope. Yeah, that's right. So maybe if this helps, maybe these are identical and these two are identical. So it's the same molecule. Okay, so let's do that. It's a teachable moment, I guess. Control Z, do L here. Richard, this is a good question. So the question is, if I put the bromine here, is that the question? Does it make a difference? This is 14, that's 18. Wow. I'm gonna break that down to 16. Okay, so the question is that if let's say that I didn't know that these two things were the same, did it matter if I put the bromine here or there? Actually, let me change the colors of the two A's. And the reason why I know that these are identical because they lead to the same compound. So if I had to name this molecule here, what would you tell me? To be 2-bromo what?
Butane.
Butane. And if I had to name this molecule as what?
2-bromobutane.
It didn't matter. In this case here, I have to put 1 here because I need to get my sustainement to the lowest possible number. So 1 would start on the right. But for this molecule, 1 starts on the left, again, because I have to get my sustainement to the lowest possible number. So they give the same compound. So that's how I know that these two positions are identical. Did that answer the question that popped up?
Yes, sir.
Any other questions?
I had a question, but I think that answered it because it was like basically just going back to about the numbering
Yes.
Right.
Yes.
versus it'll be left or starting right.
Yep. Yep.
Okay.
Yep. In this case here, you start one here, but one has to stay there. Those why we have those rules. All chemists have to practice them. Is that you only can generate a name when you have given your substituent the lowest possible name, and that's the way that we stay uniform in naming things. Okay, good. All right, so this is this review. I didn't want to focus on that. I'm just going to put this in a box. This is what you should know at this point. This is what your quiz is going to be about. You want to be able to make sure that you understand this level of chemistry. But this gives us a review of preparation of alkyl halides. All right, this is what chapter 6 is all about. How do we make these, and then what kind of chemistry comes from these compounds? All right. So once we have alkyl halides, now we know that we can do something called a substitution reaction. So let's kind of move into that really quickly. All right. What is a substitution reaction? So I need to break down the two classes first before we move any further, and then we'll start to do a real example. All right. So there's two mechanisms that can come from a substitution reaction. I'm going to put a bromine here. I'm redrawing something I already made it. Give me 1 sec. Let me add this student into the class. All right. So the note that I'm trying to make here is that there's two mechanisms, two possible mechanisms for substitution reactions. All right, let's cover the two possible mechanisms for substitution reaction. All right, in one mechanism, my nucleophile, and I'm going to use the word nuke here, and I'm going to give it a lone pair because nucleophiles need electrons. We're going to define those shortly. All right, can come and attack and kick off the BR. All right, so everything happens in this step at one time. Let me see if I can get a good color on that nucleophile. So one step process. All right, the nucleophile attacks carbon with the halide, while at the same time the halide leaves. Okay. Is everybody comfortable with that one-step process here? Let's look at
that one more.
Okay, so that, you want me to say that one more time?
Yeah, you were breaking up.
Okay. I'll say it one more time.
Breaking up.
Okay. I'm breaking up. Is it better now?
Yeah, it's better. I can hear you.
Okay.
Yeah.
The nucleophile is going to attack while the leaving group leaves, all in one process. All right, so that's what I'm trying to say for this first mechanism type. The one process. Nucleophile attacks, leaving group leaves. All right. The second potential step, let's make this a little bit bigger. Let's make a line here, is where I get two steps. First, the leaving group has to leave, and it generates a very important intermediate here. Excuse me, having some issues real quick. So the leaving group leaves to form this intermediate here that has a plus on the carbon, we'll come back and talk about this. Then the nucleophile attacks. Right? To make a, actually, I won't show that product yet, but I'm going to show that the nucleophile attacks this intermediate. All right, I hope that makes some sense there. Okay, let's go ahead and let's write this out. So this is a two-step process. First, the leaving group leaves, or in this case here, sorry, I can't use that word yet. The halide leaves to form a reactive intermediate known as a carbon cation. I'm sorry, a carbon cation. Then, in the second step, the nucleophile attacks. Carbon cation. Okay. So is everybody kind of making some sense of this? I'm going to repeat both to make sure we're comfortable first.
Dr. Gilbert, I just have one question. So is this saying this is two possible ways we can work it, or we'll have to figure out which way we need to work it?
Yep, there's two potential ways, and you're going to learn which way is going to dominate the chemistry.
Okay.
Yeah, that's coming up next. How do I know which mechanism to use? All right. So let's repeat.
So with that, disappeared in the second step with the help of what? Or we substituted it, let me say that, with the help of.
Yeah, to solve, or well, I'm trying not to get there too far, but there are ways where this will pop off by itself. All right. So that's the difference initially that we want to see. Okay. Is that to do a substitution, there's two ways it can happen, right? One way a substitution can happen is that your nucleophile can approach the carbon that has a halide, and that will go ahead and make its bond while the halide leaves. All right, so that's one possible mechanism way. And the other possible mechanism way is where the leaving group, or the halide, this leaves on its own, and then the nucleophile just finds a molecule that is missing a bond, and then it makes a bond there. So that's another way you can substitute. So hoping you guys are getting comfortable with that. The nucleophile can approach, and then the halide leaves, and you get that substitution happening that way. Or the halide just falls off on its own, and then the nucleophile replaces the bond then after that point, right? So these two mechanism types are what you guys will have to start to study and master. All right, let me open up some more pages here. One sec. So whenever I do the one-step process, this is known as a nucleophilic substitution that is bimolecular. All right, and most people abbreviate this to say SN2. All right, so this is an SN2 reaction. Right? We'll talk about what that means here shortly. On this side, when I do the two-step process, this is a nucleophilic. Wow. Sorry. This is a nucleophilic. Misspelled the first word. Substitution that is unimolecular, or some people like to even say monomolecular. Okay. And this is referred to as an SN1 process. Okay. So let's define a nucleophile and then let's go back and work on this. Why is this one called a nucleophilic substitution that is bimolecular? And why is this one called a nucleophilic substitution that is monomolecular? Right, that should be the question that's burning right now in your guys' minds. Okay. So let's define some words. What's a nucleophile really quickly? Can we talk about this yet in class? Not yet. A nucleophile is a
I don't recall.
molecule or atom that is seeking a positive nucleus. Right? That's what it means to be a nucleophile. Is everybody comfortable with that so far? Any questions there?
No.
Okay. And the brother or sister, I guess you would say, to a nucleophile would be the electrophile. They usually come in pairs. What's an electrophile? It's a molecule or atom that is seeking electrons. Okay. Hopefully everyone can see how these are the opposites of one another. Nucleophile needs a positive nucleus, and electrophile needs electrons. Okay. So in this reaction above, there is a nucleophile, obviously we call it nuke, but there's also an electrophilic site or an electrophile, which is the carbon that the nucleophile is attacking. So let's go ahead and work on an example really quickly. All right, I'm gonna have to change my format here. I don't like the way Monica's looking. Okay, so I'm gonna give this reaction. We're gonna try to work on the mechanism, and then we're gonna. Actually, before we do that, let's go. I think we can explain this now. So, what is a SN2 reaction? Why is it called that? All right, because the rate of this reaction, when we say the rate constant, it depends on the concentration of the nucleophile and the concentration of the alkyl halide that you're using. And sometimes I like to use the word substrate. Right, there's going to be some other compounds that do SN1 reactions that won't have a halide. So that's why it's safe to say substrate, right, which is one of your starters. All right, so let's kind of see if we can break this down really quickly. What does that mean? If we look at the one-step process, if I add a larger amount of nucleophile, the reaction is going to go faster. If I add a higher amount of the halide, the reaction will also go faster, right? So we know that that means that the whole process, this whole substitution, depends on both substrates or both reagents. I need a nucleophile and a halide present to really get this reaction going, all right? So that reveals to us the mechanism, right? Both components are important for the mechanism, right? Both of these things need to meet each other to react. All right, does that kind of help? Let's go ahead and make some notes down here. This is what you guys want to keep in your mind here. If I increase concentration of the nucleophile, this will always lead to a faster reaction. And the same thing if I increase the concentration of the alkyl halide. Right, that also will lead to a faster reaction. All right, let's look on the opposite end of that. What's going on with if I do the unimolecular substitution? All right, this is really telling me now that the rate of this reaction depends on one thing. That's why it's a unimolecular reaction, and that's only the concentration of the alkyl halide. Okay. So that means if I increase the concentration of the nucleophile, what happens here? Nothing.
It's a slow.
Nothing happens. Right? So if I increase the concentration of the nucleophile for this reaction, nothing happens. If I increase the concentration of the alkyl halide, what happens? It does get faster. Okay. So what is that telling us about the mechanism? What does that tell us? It tells us that this mechanism depends on the leaving of this bromine or the halide, right? It doesn't matter if I pump in a lot of nucleophile. It's not going to speed this reaction up, right? Because the nucleophile can just sit here and do nothing, right? It only can react when what happens? Once I form this carbon cation, right? Or once the halide has left. So that's how we know that this reaction occurs this way, because the reaction depends only on the alkyl halide, right? If this doesn't leave, the reaction doesn't work. So this is why this is important. Adding more of this compound can increase the possibility of having more of this leave, and that can indirectly or directly affects the rate. It'll make it faster. But the nucleophile has no influence over the reaction because the rate determining stuff is leaving of this halide. Okay? So that's our clues in determining the differences in the mechanisms, right? What influences the rate of the reaction? All right, there's some other influencers that we're going to get into as well. All right, but let's, for now, we have the fundamentals down. Let's start working on a mechanism for these reactions. So I'm going to use the same alkyl halide. In this case here, I'm going to give you guys a real nucleophile for now. I'm going to give you, what's a good nucleophile to try? Because everything can be. I'm going to use lithium hydroxide for now. Even though you guys know this as a base, that's going to come up shortly as well. All right, we're going to use lithium hydroxide, and I'm going to use a solvent called acetone. And for now, I think most of the class, you guys know what acetone is. All right, we're going to talk about why all these things are important here shortly. All right, if this is the nucleophile, keep in mind, and I probably should go ahead and do this because it's the first time we're doing this, that this is an ionic compound. So lithium is going to carry a plus charge, and the hydroxide group is going to carry a what charge? Anybody know?
A negative.
That's right, negative charge, right? And we're going to start to work on defining nucleophiles here shortly as well. But all nucleophiles are going to carry electrons. They're going to either have a lone pair or they're going to have a minus charge. So I'm going to do the mechanism. You guys are going to tell me which mechanism I just completed. So in this mechanism, I want my hydroxide anion, its lone pairs, to now attack a carbon. All right. And the carbon that has this bromine is going to leave. Give me a sec here because I need to modify arrows a little bit. Okay. I'm going to color that red. Color that red. All right, and there's some features here that we want to make sure we got down. I'm going to try to review that shortly. All right, and once I show the mechanism for this, instead of having a ER attached to the ring, now I have a what?
OH.
OH. I'm going to color that purple. I'm going to color that red. All right. And I'm also going to form in solution this compound here, lithium bromide. All right. So this was happens. All right. That's what's going to happen to your leaving group. This is going to form a salt. Right. There's lithium that's still looking to pair with anything negative. Okay. So which mechanism was this that I just drew here?
That's one step.
This is the one-step mechanism, and this is called which type?
SN2, the bimolecular.
Yeah, this is the SN2 reaction. That's right. Very, very good. Let's go ahead and make this a little bit bigger. This is the SN2 step. All right. Know this is your first introduction to this, but is everyone kind of getting comfortable with how this is working so far? This first step is the SN2 step, right? The lone pairs on my nucleophile attacks the carbon that has the leaving group, or I'm sorry, the halide. This halide breaks. I replace it with a bond to OH now, and my leaving group is bonded to lithium. Okay, good. Very, very good. All right, on the opposite end of this, I could have taken this same compound I'm going to use the same nucleophile. Right? I'm going to change the solvent now to H2O. It's the same thing as saying what here? This is water, right?
Water.
It's water. All right. And if I do it in water, my mechanism changed. Now, my first step, actually, I need to borrow my arrow. It's a little bit cleaner. Now, my first step is my leaving group leaves, or the halide leaves. And I form this compound here, which is known as a what? What's the name of this compound?
Butane.
This is a carbon cation intermediate, right? Can anybody tell me? Actually, I want to make this all caps. It's very important. All right, don't forget, all reactant intermediates can be classified. So let's put a note here. What's the classification of this carbon cation? And what am I asking here when I ask for the classification?
Like primary, secondary.
Yep, that's right. So how do I even start a question like this? first find the functional carbon, right? And I gave you the word carbon cation. So that means find the carbon that has a what charge? A plus charge, right? That carbon there. And then from that carbon, how many carbons are attached to it? So how many carbons are attached to the carbon that has the plus?
2.
That's right, 2 carbons. So that makes this carbon cation classification change to what? What would I call this?
Secondary.
This is a secondary carbon cation. All right, that must mean that this means something to us very soon, right? For me to go through this exercise, it means that I need to know how to classify these reactive intermediates. And a carbon cation, you will classify this as a what type of intermediates? Electron rich or electron poor? Carbon cations are electron poor, right? They don't have a full octet. That's why there's a positive charge there. So keep that in mind. All right, that's going to come up very soon here. We want to, carbon cations are going to try to stabilize themselves if they can. So if I'm secondary, but if I can become tertiary, benzylic, or allylic, it's going to do whatever it can to make that happen. We're going to see that shortly. All right. So this secondary carbon cation, unfortunately, is stuck. It can't do anything else. So what happens next in the mechanism is what? Did anybody remember? Now my OH minus and attack it, right? All right.
Is this how this is supposed to be drawn, or are you drawing it for room? Like how you have it going down and then back up?
Yeah, you can draw this way, or
Okay.
you can draw it in a straight line. It really depends on however you want to draw it. But you need to show that the leaving group leaves, carbon cation forms, and then this hydroxide is attacking. And that's going to give me this product here. Okay, and you're probably going to form a little bit of this. I think this is insoluble water, but this might dissolve in water, but it doesn't matter. Okay, so because I went through 2 steps, what's the mechanism type down here?
SN1.
This is an SN1 process. Very good. I need something pretty light. Okay, good. So we got the SN2 mechanism, all one step, and then the SN2 mechanism.
So we won't have to know how to draw all of this. We just need to be able to identify.
No, you need to draw the mechanisms. You do need to draw the mechanism. Right now, this is just trying to introduce the mechanisms. But you need to know how to draw the mechanism for each step.
Okay.
Okay, good. So far, we're starting to get some clue about what's happening in the solution, right? One just has everything happening at the same time. Another one has this intermediate that forms, then the nucleophile comes in and attack, right? So the first question before we start to solve problems is this. How do we know which mechanism predominates or influences, I guess you would say, chemistry? Sorry. Influences is probably better to say. All right, how do you know which mechanism influences the chemistry for product formation? All right, so we need to know what forces a reaction to go SN1 or what forces a reaction to go SN2. Let me try to make this a little bit smaller here. All right, and there's two main influences of the mechanism. The first, hopefully, that you guys saw here was solvent. I'll make it all caps. Right. Can anybody define a solvent for me really quickly? What's a solvent? If I had to ask you to define solvent, what would you tell me? Okay, no one. There's two words that come. There's another word that comes to mind when I think of solvent. I would think of the solute. What's the difference between the solute and the solvent?
The solute is what's dissolved into the solvent.
Okay, sure. The solute is what's dissolved. So when I think about something being dissolved in something else, typically I think about amounts, right? So the solvent will be in which category when I think of amounts? Would it be the larger amount or the smaller amount?
Larger.
Yeah. The solvent is typically the larger amount. Now, sure, you can mix something equally. In that case, there's not a lot of cases where we do that, but there's cases where you take equal amount of the solute and equal amount of the solvent. But typically, when you have more of one substance that you're trying to make a mixture of, it's going to be the one that's in larger amount would be the solvent. All right. So solvents in these cases here are in so large amount that they have a very big influence over the reaction. Right. And so here, acetone and water have two different effects. Hopefully you guys can see that water has a protic H that will encourage hydrogen bonding. And a lot of times there's lone pairs on these molecules. They can hydrogen bond with the solvent, and that causes this bromine to be attracted to the solvent, and it helps pull it away. All right, so this is why this solvent helps this leaving group forms a carbon cation. However, acetone is a compound that doesn't really do significant hydrogen bonding, so this bromine doesn't have really any affinity for it. So typically, it's just going to stay attached to the carbon, and so this forces a nucleophile to have to approach to kick this off, versus where this solvent can help pull it off. All right. So this is why solvents influence the mechanism. The second thing, and we're going to break that down, we're going to tell which solvents do which type of chemistry. And the second thing here would be the features of the alkyl halide. There are some alkyl halides that are that prefer to do an SN2 mechanism than others, and there's some alkyl halides that prefer to do SN1. So we'll talk about these two things here. These are the two big influencers. But lastly, I guess just to cover my bases, really the reaction conditions. All right. So you can modify your conditions to wherever you think appropriate to also influence the mechanism. Okay. So we need to start to work on how to recognize nucleophiles, and I need to identify alkyl halides and then just break this down into which type does what. And hopefully I can end in 2 minutes here with an example. All right, so nucleophiles are going to contain negative charges or lone pairs. Okay. A strong nucleophile has a full negative charge, and strong nucleophiles always prefer to do SN2, right? And that makes sense, right? If the nucleophile is influencing the chemistry, strong nucleophiles are going to be preferred for SN2 reactions, all right? So that means if you're a neutral charge, it means that you are just a mild nucleophile. Right? You're not going to be strong. Is there any questions with the nucleophile really quickly?
So like lithium hydroxide was a mild nucleophile because it was.
No, this one, that was a strong nucleophile. There's a full negative charge on the oxygen.
Oh,
So
okay.
ionic compounds are typically strong. They're going to be very strong. That's good. All right, I'm gonna try to get to a few examples. One example of that. Well, I'm gonna do two. I need to contrast. Okay, the second thing here that we want to start thinking about are alkyl halides. Right. So if I'm a primary secondary, allylic, or a benzylic, I don't mind doing an SN2 mechanism. However, if I'm an alkyl halide, and I'm tertiary, secondary, allylic, or benzylic, I don't mind doing the SN1 mechanism, right? So that seems like, well, that doesn't help. But there's, in one case, it does help, right? And let's see if we can figure it out. So that means for the SN2, I cannot react at what type of alkyl halide? Everybody see? At tertiary alkyl halides. All right, I can never do an SN2 reaction at what type of alkyl halide?
Tertiary.
Tertiary alkyl halides, all right? And I cannot do a SN1 at which type?
Primary.
Primary alkyl halides. All right, I'm going to put a star here because if there's a potential resonance, then that changes things. But in most cases, I cannot do a SN1 at a primary alkyl halide, right? Unless, exception, I would say, with resonance. Okay, is everybody comfortable with that so far? All right, so that's going to be a big help to us, is understanding what's going on with the alkyl halides. All right, let's break down our solvents, and we're almost there. I know I always seem to be running out of time. Never enough time in the day. So all right.
Dr. Cooper, is that word right there supposed to be accept?
Sorry. All right, my computer froze. All right, give me. Is it working? All right, I might be. I hope I'm not done for the day. I need to finish this thought. Okay. All right, let's work on SN2 solvents really quickly. All right, my SN2 solvents are a class of solvents that are known as polar aprotic. All right, and aprotic just means no acidic hydrogens. So whenever I see a polar aprotic solvent, all right, I'm really indicating that I want things to be done doing the SN2 mechanism. All right, so let's name a few of these really quickly. I'm going to have to give you guys a structural list later. DCM, this is a carry it all the way out here. Just dichloromethane. You've been in lab, you guys have used this. All right, acetone. You guys know what acetone is. DMF. Right, and this stands for N dimethyl formamide. THF. Tetrahydrofuran. I'm trying to think if there's anything else that's important. And that's it. DMSO is a good one. That should be it. Dimethyl oxide. Those are all the major polar aprotic solvents. All right, and again, these solvents are going to predominate chemistry for SN2 types. All right, there's a solvent types for SN1. Right, and these are going to be known as a different class that's called polar. Again, they're polar, but they're going to be polar protic. What do you think that means? These contain acidic hydrogens. All right, so this is going to be solvents like water. All right, I'm going to make in red that acidic proton that's present. Ethanol. And methanol. All right, so that's kind of a trick that you can use to help to remember if a solvent is polar aprotic or polar protic, right? And that's just going to come just from looking to see if that solvent has an H, right? DCM, acetone, DMF, THF, and DMSO, all right? Outside of THF, they don't have that H present, all right? THF does, you just have to remember that. But water, ethanol, and methanol, they all have an H in the name, all right? And that lets you know that that solvent is protic, right? So the solvent is going to have one of the biggest influences, right? And one of the heaviest influences I like to use in determining whether a reaction is going to go by an SN1 or an SN2 mechanism. All right, let's end with trying to determine if a reaction is going to go SN1, SN2, and see if we can generate the product. All right, next class, I'm going to try to break down more about the nucleophile or the potential nucleophiles we can use. That example here. Okay, I don't know what I just did there. All right, I'm almost there. Sorry for the wait. Okay, let's work on some questions really quickly before we end today's class. Can we identify these three or these important features? All right, first, can you tell me what type of alkyl are classified alkyl? Two, can you classify or identify solvent type? Three, can you provide nucleophile? Sure. And the last thing, obviously, will be to predict. All right, so let's go through these really quickly. So for example A here, or the example up top, can you guys tell me what type of alkyl halide are we starting off with? Can anybody help me out?
I mean, like a tart butyl.
Oh, no, classified as primary, secondary, basylic, allylic, right? So how do we do that? We look at the carbon that has the halide right here, right? And to that carbon, how many carbons are attached to it?
3.
All right, so what type of alkyl halide is this?
Tetrary.
All right, good. Is there anything else to it? Is it benzylic, allylic?
No, sir.
Okay, good. So this alkyl halide will be classified as a tertiary All right, this is a tertiary alkyl bromide. Can you guys help me with the next question here? And it's, can I identify the solvent type? What type of solvent do I have?
SN1.
It's a pro.
Yeah, this one is polar potent. Very good. And I heard somebody say what type does polar potent like to do?
SN1.
Yeah, this refers to SN1 mechanism. Good. All right. Can you guys help me? Actually, this is not going to work the way I wanted it to. Let's go right here. Can you guys help me identify what type of nucleophile do I have? Is it strong or weak? Mild, I guess you would say.
Weak.
Yeah, this is we'll call it mild, but this is mild to weak. And how do you know this is mild or weak?
It doesn't have a negative charge.
Yeah, definitely. You guys are doing good. All right, so mild to weak nucleophile. I have a polar product solvent, and I have a tertiary alkyl halide. I meant to put this here. Which mechanism type would be preferred here?
SN1.
Yeah. Head on. This is definitely asking for an SN1 mechanism. All right, if there's any questions, just have an opportunity to go back through the notes here, and you will see that all the solvents, the strength of the nucleophile, and the alkyl halide, right? Maybe I should go back. Tertiary alkyl halides, SN1, right? Mild to weak, I didn't put this here. I'm sorry. I'm glad I went back. It has to be SN2. Sorry, SN1. So we're here. Okay. And if I have a polar aprotic solvent, I'm going to further be SN1. All right. So I just need to be able to draw the products. My phone is going crazy. I think I have a meeting coming up. All right. And all that has to happen here is that the bromine gets replaced with an oxygen, and all its atoms are carried over. Right. I know this is new for you guys now, but we'll talk about it. The H on the alcohol has to leave. Right. That can't stay. And so this would be your final product here. Okay, actually, I need to make that any bigger than what it was. All right, so for now, we'll work on this mechanism. This mechanism is coming up soon. All right, but that is the final product from that reaction. Okay, what's happening here? Can we break this down before we leave today? What type of alkyl halide is this?
A phenyl.
Oh, I'm just asking for classification, not any alkyl.
Oh.
It's a primary, secondary, allylic, benzylic. So how do we do this again?
Primary.
Okay, good, very good. I look at the carbon that has the halide, right? And how many carbons are attached to that carbon?
One.
Just one. All right, is there anything else special about it? Is it benzylic or allylic?
No.
Very good. All right, I was trying to trick you guys, but you guys found it. I put a phenyl down here. I wanted somebody to say benzylic, but this carbon is not attached to the benzyl, right? So it's not one away. Instead, this is two away. All right, and there's no name for that. All right, there's no convenient name. All right, so this is a primary, alkyl halide. Very good. What type of nucleophile do I have? Is it strong or weak? Can you guys help me out? I'm moving fast because I'm over my time. This is a strong nucleophile. Can anybody explain why this is strong?
Because it's because it's polar aprotic.
Oh, the nucleophile, not the solvent.
Because there's a plus charge.
Doesn't have it. Well, yeah, it's charges here, right? It's ionic. All right. When I draw this line to a lithium, you guys do know that carbon and lithium are an ionic bond, right? Carbon is non-metal. Lithium is a metal, so that bond is really ionic. So there's a negative charge on this carbon and a positive charge on the lithium. So because the carbon carries a full negative charge, this is an extremely strong nucleophile. All right, in my solvent, what's the solvent type here? This is polar what?
Bariatic.
Yep, polar aprotic. That means I don't have that acidic proton. And so all these conditions are favoring which mechanism type?
SN2.
This is favoring SN2. All right. I know we're just working on this skill today, right? But we want to be able to predict the product here. And if I had to draw my product.
So would you just connect all of that lithium to that where the I was?
Yep. Sorry, not to make long bonds on that. Yeah, I'm gonna get this compound. Don't forget, students like to see. I'm an organic chemist, so I don't care about the inorganic materials. But if you want to, you can. It's gonna be a lithium iodine that's also gonna be in solution. All right, but because this is organic chemistry, I don't really care for knowing what happens to the inorganic stuff. So that lithium and the iodine are gonna partner. But the major product I'm interested in is the organic stuff, and that would be your final product there. Okay, so what we're gonna do next class is that we're gonna continue working on drawing the major product. All right, we need to talk about this mechanism when I have a weak nucleophile and I have an H here. What happens to the H? So we'll start talking about that. That's a mechanism that we need to know. And then we slowly started to talk about this, but we need to get into this. This carbon cation has some unique features that we need to start to study. All right, and then we'll be finished with our S or our substitution class of reactions. Then we're going to move into chapter 7 that talks about the opposite of substitution, which is an elimination. What happens if I eliminate something? What does that look like? Okay. I will see you guys next class. Really quickly, let me end the recording. Then I will take any questions